Coherency, verification and deadlock detection using a Perspec bottomless stimulus. Abstract, modern SoC, designed for automotive and mobile application, typically has multiple processor cores, multi-level cache hierarchy, and subsystems that share memory and system resources. Cache coherence and deadlock avoidance are two critical areas that are needed to verify for this type of design. This paper described how portable stimulus standard PSS and EDA tools, such as Perspec, were used to shorten the design verification of the two areas, memory coherency and deadlock avoidance. Introduction. Many system-on-chip (SoC) designed for automotive and mobile application consist of the multiple processor cores and IP subsystems that share the SoC resources such as memory, system interconnect (IC), and I/O subsystems. The effort required to manually create a sufficient test suite to verify such design is significant due to the number of processor cores, number of coherent I/O masters, multi-level of the caches, and various combination of how these processor cores and I/O masters can access memory and shared resources. EDA tools and reuse methodology can help reduce the time and effort required to implement the test suite. With the release of the Accelerator Portable Test and Stimulus PSS version 1.0 in June 2018, the SoC level verification automation tools and test scenarios reuse will significantly improve similar to what UVM has done for IP levels verification. There are many papers, articles that discuss the cache coherency too and how to tackle this issue, the protocol level and block level and SoC level. The main contribution of our paper is to discuss our experience with using PSS and how to PSS and EDA tools such as Cadence Perspective System Verifier help to shorten the design verification cycle of this type of SoC into specific area, memory coherency and deadlock and live log and detection. It was achieved by taking advantage of test generation automation and coverage collection capabilities provided by the Perspec and the reuse of the PSS scenarios from the project to project. For coherence testing, we also reduced our verification time further by building our coherency test suite using the action provided by the Perspec coherency library. Deadlock detection is another area that we focused on in this project. Deadlocks are caused by the coherence protocol violation, such as PCIe. Deadlocks occur only when the specific sequence of transaction and the timing occurs. It is difficult to do root cause analysis when the deadlocks occur at the post-silicon level. It is also very costly to uncover these issues at this late stage of the project. To ensure that our design is free of deadlocks and uncover any such issues before tape-out, and we have created a deadlock detection verification environment to verify the root cause of the deadlocks at the simulation level. Deadlock detection testing presents a unique set of challenges and requires specific features to be added to the verification environment to detect the deadlocks and to handle this deadlock event automatically when they occur. To check the deadlock condition and to handle it automatically, we set up an auto-regulation test suite and implemented the following monitors in our verification environment. The system monitor receives periodically heartbeats response from a CPU, which indicates the normal CPU operation. Missing heartbeat responses from a CPU after the predetermined period of time will indicate to the system monitor that a possible deadlock has occurred. When a deadlock occurs, a system monitor will send a deadlock alert to the system tracker. The transaction latency monitor, which recorded the transactions latency, and this recorded data can be used later to determine the transaction can cause the deadlock. the system tracker which captures the system rate, the relevant signals for the post-run, root cause, analysis of the deadlock condition. We will be discussed following the topics in the more details in the paper. Overview of the typical automotive SoC architecture using the Perspec library in the PSS scenario for the coherency verification, deadlock detection, verification environment, and auto regression test suite. PSS scenarios to PCI deadlock conditions, result and lessons learned from an actual project. Overview of the typical automotive SoC architecture. Due to the computational demand on the advanced driver assistance system, ADAS, coupled with the need to do real-time imaging processing, pattern recognition processing, and other cognitive computing related tasks, the SoC designed for automotive applications requires a large number of process cores, one or more graphic processing unit, GPU, and a neural processing unit, NPU. And these processor cores, GPU and NPU, or share memory resources. Interconnect bus and I/O subsystems, for example, PCI and Ethernet, USB and USB, etc. The figure 1 shows the block diagram of the typical SoC for automotive application. There are multiple processor cores organized into multiple clusters. To reduce the effect of the shared memory bottleneck, there are multiple levels of the caches. Each processor core has its own private Atom cache, as shown in this diagram. Each processor cluster has L2 cache shared between the cores and the cluster. Some design even in the LLC, last level cache, which resided in the Coherency interconnect, is shared between the all processor clusters and the other coherency masters, such as the GPU. Figure 1. A typical SoC architecture or for automotive application. All the process cores, GPU, NPU, I prefers generate their request transaction receiving requested data through the Coherency interconnect using the AXI coherency extension and the ACE write protocol. Due to the shared resources and multi-level of the caches in the type of the design, it is very critical to verify that the SoC is free of the coherency issues and deadlock issues. In Section 3, we will discuss our approach for coherency verification. Section 4 and 5 will cover our approach for deadlock and deadlock and verification and Perspec of the PSS were used to speed up the test scenarios development and to facilitate the reuse of these test scenarios for future projects. 3. Using Perspec library and PSS scenarios for coherency verification to ensure that there are no coherency issues in the design, we created a set of coherency tests in the consists of the force sharing test, true sharing test, exclusive access test, and the DVM, distributed virtual memory test. We use the Perspec library and its utilities to speed up the development of the above test scenarios. Perspec libraries provided a basic memory read and write actions, coherency actions, and a built-in test suite for memory and coherency verification of the processor memory subsystem. For the remaining of this section, we will go through the process of creating our processor memory model and the PSS scenarios using an atomic actions provided the prospective coherency library and how to write reusable PSS scenarios. What we are hoping to convey here to show how to EDA tools, for example Perspec and PSS, helped speeding up the test development and also allow the use of the PSS test scenarios from project to project. That the test development process consists of the following steps. model the compute, processor, memory subsystem, develop memory coherence test scenarios for the computer system, develop PSS model for the other subsystem. For develop subsystem, the test scenario, we will only go through step 1 and 2 in the section. Step 3 and 4 will be described in section 4. PSS scenarios to detect PCI deadlock condition. Step 1. Model the computer subsystem. Most computer subsystems for mobile and automotive SoCs are based on the multiple core processor and interconnect architecture. The difference between them are mainly the types of the processor used, the number of cores, the number of clusters, the cache coherent hierarchy structure, the memory types of sizes. For this reason, the computer subsystem PSS model and each supported actions are suitable candidate for encapsulating in a user and configuration library. And this is what was provided by the Perspec. Using the PSS Perspective Coherency library, the modeling process of the computer subsystem requires no coding. We just need to fill out the information related to process cores, the clusters, the memory type and sizes, the cache structures, and etc. In the Perspec configuration tables, these tables were captured in an Excel CSV configuration file, and this modeling process of the SoC compute subsystem was done in a couple of hours. Most of the time was spent tracking down the information required to fill out the prospective configuration tables. The table 1 and 2 shows an example of the processors and the memory configuration tables. The table 1, processor info table. This table describes the processor subsystem of the design. The column in this table presents the attribute of the design. Some key attributes are num tag, name of the processor cores. There are 12 of them, M0 to M3. Number of kind, the kind type of processor. Number of cluster, name of the processor clusters. There are 3 of them, M0, AP, A72. Table 2, memory info table. This table specifies the different memory blocks and their address ranges. In this example, we have 3 different memory blocks, DDR0, DDR1, DDR2. All of them are enabled in the design enabled column. Note that the simplified discussion, we only show the key columns, that is attribute table 1 and 2. Users can add additional columns and attributes to these tables that are specific to their design. Processor info table 1, processor info table. Table 2, memory info table. When these configuration tables were filled out, we were able to bring the Perspec and created a memory and coherence test using each GUI, graphical user interface, and writing the PSS code directly. Step 2, develop the memory coherency test scenarios. In this step, we created a simple memory read and write scenarios first to ensure the processor memory subsystem was working correctly. Once the Beijing memory read and write per operation were functional, we created more complex force sharing and truth sharing and DVM test scenarios. We also used in the built-in coherency test suite of the Perspective's coherency library, reviewed the coverage result, added additional tests to achieve the desired coverage. In the remaining of this section, we will show the some people PSS memory read and write scenarios to illustrate how to write reusable PSS scenarios using the action and the utilities provided by the Perspective libraries. Figure 2 shows a simple PSS memory read and write scenario using the atomic actions provided by the Perspective SML library. 2 solutions of this scenario are shown in the figure to illustrate how to test generate from this scenario. This PSS scenario is simple, but it does illustrate some important points. SM1 underscore process underscore tag underscore E is an enumerated type created automatically by Perspec using the tag on the shop tag column in the process info table. It consists of following values: M0, M1, M2, M3, A02, A3, AP02, B3. 자, write underscore data, copy underscore data, read check and data R, read underscore check underscore data R, atomic action provided by the Perspec XML library. The PSS action, PSS WRC, PRC can be usually used by the other project, even though these projects might have a different processor and memory configuration. Note that the in-generation test, PORC underscore tag, process cores, mseg error, memory buffer address, and memseg block tag, memory block ID are randomly picked by the Perspec for the test solution. So we can use this PSS WRC PRC action as a building block for more complex PSS scenarios. Figure 3 shows the code of the PSS WRC PRC 3 cores action. This action uses the PSS WRC PRC action to create a scenario that has 3 processor cores doing write data, copy data, and read check data in parallel. The action PSS WRC PRC 3 cores has 3 knobs: PORC DAC 2 and 3. These control knobs will know the test writer to select the process cores to be used for his test. Notice always that there are 3 constraint statements encoded to ensure that the processor cores selected by the test writer by our perspective will be unique, since these cores are executing the PSS WRC action in parallel. Figure 4 shows an example of the force sharing scenario. Force sharing IW-based action executing in parallel to our PSS WRC PRC action. These scenarios illustrate 2 other convenient features. SM1 processor subset select S is a control knob structure automatically created from the processor input table. This control knob structure consists of all knobs that are allowed to test writer to select the process cores, the clusters, etc. to be used in his testing. The constraint for each in the code ensures that the process core selected for the PSS WRC PRC action will be different from the core selected for the force underscore sharing the RW based section. 자, figure 3, example of the more complex PSS scenario using the PSS WRC PRC action. 자, figure 4 is a force sharing scenario using the perspective CND coherency OPSC library action and our PSS WRC PRC action. The 4, the deadlock detection, verification, environment, and auto-regulation test suite. The purpose of the deadlock detection, verification, environment is to verify the known deadlock conditions are produced by the test suite. Depending on the SoC configuration and design, a deadlock may not occur even though the deadlock conditions are recreated. In this case, we can confirm that a deadlock condition could occur through the coverage measurement result and that the SoC is free of the deadlocks. Figure 5 shows the block diagram of deadlock detection, verification environment. If a deadlock actually occurs, we can use the deadlock diagnostics feature described below to identify the debug cause of the deadlock. A system monitor, a status check timer is used to generate periodic interrupt to the CPU. When this interrupt occurs, the CPU checks the status of the system and sends a heartbeat response to the system monitor. In the case of SC error, kernel's panic, live lock, or other failure, and the CPU will deliver a failure response instead of a heartbeat response to the system monitor. If there is no heartbeat response from the CPU, after a certain period of time, the system monitor considers the CPU to be deadlocked and will inform the system tracker. 2. Transition latency monitor. During the execution of the scenario. The transaction latency monitor records the latency of all transactions originating from the CPUs. If the system monitor has detected a deadlock, the transaction latency monitor will pass the information about the oldest transaction that has not completed the system tracker. With this information, the system tracker will be able to infer which transaction and which method caused the deadlock. The system tracker, the system monitor has detected the deadlock. The system tracker will start gathering the following information for root cause analysis. The CPU status, PCs, GPR, P-state, fault status, exception, error, syndrome, register, and ledger, etc. Count test scenario, information about the suspected transaction, estimated time when the deadlock occurred. After gathering this information, the system tracker will create a log file and the simulation manager manages the whole process of the creating and executing the prospective scenarios for simulation and analyze the result. After the simulation has finished, the simulation manager will fetch the log file from the system tracker specifically for the deadlock cases and will perform a waveform dump around the point where the deadlock occurs using the save and restore. Figure 5. Deadlock detection, verification, environment. There are 5 PSS scenarios to detect PCIe deadlock conditions. According to the PCIe ordering rules, non-positive request I, that is, reads and configuration right to a PCIe slave interface might be stored while the posted writing from the corresponding the PCIe master the interface is restored. This is because read or write completion is unable to overtake to the posted write that is enabled to leave the master interface. This potentially can cause a deadlock condition when the write combination is timing of the PCIe transactions with the cache snoop transactions occur. There are design guidelines from the process course vendor how to prevent deadlocks. However, we do need to verify that our design is free of deadlock. The test scenarios to verify that the design is free of the deadlock and it's difficult to write manually to do the multiple parallel activity from the different masters and slaves and the variation of the timing of the transaction. Figure 6 shows the block diagram of the design that we will use to illustrate a simple scenario that can create a deadlock. The figure 6 block diagram of the design used to illustrate the potential PCIe deadlock condition. Yes, a possible deadlock condition can occur in figure 6 it as follows. The CPU cluster performs a number of non-posted reads from a PCIe endpoint, EP. These non-posted read requests will fill up the PCIe RC request buffer. The PCIe cluster performs a number of non-posted conflict write to the PCIe endpoint EP. These can be offsetted because the non-posted request channel is now saturated due to the previous non-posted reads in step 1. The CPU cluster generates a write back of the address A. The write back cannot proceed because the write channel has been blocked. PCIe endpoint issues a read of the address A, and if PCIe EP issues read 1 a transaction for address A, the coherent interconnect will generate read once snoop transaction onto the CPU cluster, but this snoop can't proceed because of the outstanding write back. 5. PCIe endpoint issues a number of coherent reads, and these reads once the transaction will fill up the snoop queues. PCIe endpoint issues coherence write WLU of the address A, write line is unique WLU transaction will generate the clean and invaluated snoop before memory update. This snoop can't be delivered to the CPU cluster because the snoop Q has been saturated. 7. Deadlock is now achieved. Okay, as you can see, even for this sample deadlock test scenarios, it's not easy to create a test manually. However, using the PSS perspective, the code is pretty simple since the PSS syntax makes it easy to describe the scheduling of the different actions, and Perspec handles all the resources scheduling and constraint randomized automatically. The pseudo code for this scenario is as follows. The figure 7 shows the one of the tests generated from the above scenario. Note that the setup step is not shown in the figure 7, since this step is straightforward, and the UML diagram is smaller and easier to understand without setup steps. Figure 7, one of the generated tests from the PCI deadlock scenarios. Just 6. Result and lessons learned from the actual project. The 5. Result and lessons learned from the actual project. We have completed generation and learning of the Coherency test suite on our design. This task was completed quickly since we took advantage of capability provided by the Perspec Coherency library, and we were also able to reuse the Perspec scenarios developed on the previous project. Regarding the PCI deadlock scenarios, we are in the process of learning these scenarios to verify that our design is free of deadlocks. We were also developing more PCIe scenarios to verify our design further at the SoC level. We should be able to discuss the final result of the DVCON2019 in February. Preliminary results showed our Perspec and PSS helped us to shorten the design verification cycle significantly. This was especially true in the case of coherency verification due to the availability of the perspective coherency library and the result reuse of the Perspec scenarios from the previous project. We also learned that writing PSS scenarios were a lot simpler than writing C code manually. Also, Perspec library helped with this reuse of the test scenarios from the project since it automatically created the data types, structures, and the model of the processors and the memory systems to create reused scenarios. We did have to make a conscious effort not to refer to the actual name of the processor and memory sources in these scenarios, since these will change from the project to project. One of the lessons that we learned from these is that created portable stimulus scenarios, we need more than our PSS language. We also need a methodology and library. This is similar to the UVM, where a methodology for building reusable verification component is also part of the standard. The 7 summary. This paper shows how PSSN EDA tools such as Perspec can be used to speed up the design verification of a multi-core SoC in 2 specific areas: memory coherence and deadlock detection. These main technical contributions are application of PSS to typical SoC level verification tasks, horizontal project-to-project reuse methodology with PSS, deadlock detection verification environment. Okay, thank you for your time. I read the DVCON2019 coherency verification and the deadlock detection using Perspec portable stimulus. Thank you. See you next time.